I'm Montana Morse, the Director of Advanced Analytics and Innovation with KCF Technologies. Wanted to take some time this afternoon to walk you guys through a few things that we've been working on at KCF that I think personally are really interesting as it relates to advanced analytics in the acoustics and vibration realm. With that, I figured we'd kick it off. I'm gonna share some slides, walk through a research example that is something that KCF is looking to break into. And yeah, without further ado, here it is. So today we're going to talk a little bit about creating simulated IoT environments with generative adversarial networks. The presentation is going to be a pretty brief conceptual overview. We're going to touch on a little bit of the mathematics of the optimization problem that we're looking to solve and essentially how we're going to use GANs to create the environment that we would optimize against. But we're not going to dive too deep into the deep learning mathematics. We're going to keep it a conceptual level. Throughout the presentation, I'm going to start out with a quick business problem that will orient you towards what problem we're trying to solve and how we're trying to make an impact at KCF on the bottom line, ultimately, of the customers. We're going to take that business problem, we're going to formulate a technical problem with the sensor data that we have, which is a combination of process data, so think like RPMs on a motor, and accelerometer data when you're thinking about vibration. We're going to walk into how we might use a GAN or a generative adversarial network environment to simulate that IoT response that we're seeing in our network. And we're going to finish with a discussion around an optimization agent that would be able to learn from this environment and someday, as you'll see, automatically operate machinery. So like I said, we're going to start out thinking about this from a purely business perspective, right? So the goal of nearly all manufacturing processes is going to relate back to one simple equation, and that's profit equals revenue minus cost. If you're not making profit, the organization fundamentally won't continue to persist. So everything that we do as an organization, as it relates to acoustics and vibration, is really about providing economic value. Obviously, if you're in the research domain, you might be thinking a little bit about long-term value or long-term innovation. For us, it's really about this short to mid-term impact, where we're actually going to impact the customer's bottom line in a relatively near future. The 5 key categories I tee up here are product quality and product volume, product waste, labor cost, and tooling wear. The piece that I'm referring to when I say tooling wear is a machine that wears out prematurely, so like a bearing failure on a machine that shouldn't have had its bearing fail. So think about that kind of like depreciation. In our case, we're going to make a bunch of assumptions and we're going to simplify what we're looking at, just so that you can kind of dial into one technical problem. Now understand that with acoustics and vibration, there's ways that we could probably impact all 5 of these, but for the sake of discussion, we're going to tee into the tooling wear piece, which I'm calling over here on the right side M. And the idea is that our goal when we think about machine health monitoring as it relates to accelerometer data is to minimize the total wear over time in an industrial plant. In this quick optimization problem that's slightly oversimplified and is really theoretical, but we're going to assume that the product quality, the volume, the waste, and the labor costs must remain constant over time. In particular, when you think about volume, what I'm referring to is that we're not going to say, hey, you could minimize your tooling wear by shutting your machine off. That doesn't make sense. The idea is that we're going to assume production is constant in this environment, and our goal is to minimize the machine wear subject to a constant production volume. Now, in the bottom right there, you can realize that there is a way to break down this overarching capital M at a given point in time. So that capital M is your tooling layer on an entire factory. And the idea in the bottom right, there's a lowercase m to signify that we're looking at one asset within an entire factory, just to kind of narrow scope. But the idea is that, and this once again is a bit of a simplification, but it does get at a point that the wear on an asset is a summation of the overall vibration or any type of parameterized vibration. Say we're assuming in this case it's like the overall vibration in an individual frequency spectrum for a given point in time. So we're saying that, all right, the wear on this asset today is the sum of all of the vibration on that asset at a given point in time. We can postulate then that the wear on that asset is not only a product of the vibration at a given point in time, right? That vibration is actually a function of the operational parameters of that asset at a time period just before now. So basically the idea is that we made an operational change and the system had a function that responded to that operational change, which changed the vibration level in the machine. So really simple mechanics here, but just trying to lay down a mathematical framework that we could engage for this conversation. So you see in the top left, I have kind of the same equations that we just laid out, but what we're trying to do now is think, okay, so what we really want to do is minimize the wear on this machine. And the parameter that we have to change is, well, the operational parameters. So in this case, if you look bottom left and we're trying to minimize some function that is a response to a change in the operational parameters, or phi, really what we want to do if we were going to minimize this problem is figure out what's f prime a of phi and set it equal to 0. Now, here's the key, is we're not just trying to minimize this function for a given point in time. We're trying to minimize this function continuously over time. And when we minimize this function over time, we want to fundamentally actually change the parameters on that machine. So we're going to think about a pumping system. If we know that we turn it up and it has bad vibration, and then we turn it down and it gets healthier, we want to continuously tweak those operational parameters on that pump over time so that we remain in the minimum possible machine health, or the best possible machine health, while maintaining whatever we need in terms of production output. So when you start to think about that, the idea of optimizing operations in real time, you'd realize that it's actually a textbook reinforcement learning problem. You have an agent, which is an operator, that is taking some action, which means a change in the operational parameters on the assets, and expecting some type of response or a change in that state, where that state is the vibration on that asset. And the idea is that agent wants to take action to change the state in a way that makes the state advantageous for the agent. So what is the agent trying to do? Well, it's trying to figure out what is my optimal policy, or how should I behave at any given current state of the system? You know, in industry, or I should say in research, you'll see a lot of things about like deep Q learning. The kind of textbook first example is you have a penguin that's walking on ice and there's these different squares and it has to learn which squares you would fall through the ice. The idea is that you walk through all of these different operational parameters, in this case, in a Q learning table environment, until you figure out which pieces of ice you can step on and survive and still make it to the other side of the ice rink, I think is how that example goes. Or which pieces of ice, when you step on them, it'll bottom out and you'll fall into the water. It's the same thing, except you're trying to figure out which parameters for this pump, or better yet, which parameters for this entire factory would I be able to put our pumps in, subject to the constraints of the system, that would allow us to minimize machine health. So rather than it being a +1 for you stepped on healthy ice and a -1 when you stepped on unhealthy ice and fell through, it's some function that says this is the vibrational response that you got based on those operational parameters across the factory. And you're trying to minimize that function over time in really an infinite game. But when you think about the real, a huge problem, and this is really where KCF is starting to do research. You don't have a playground for the agent to learn the response function of the state. So really, when you're figuring out the optimal policy with deep Q learning, what you're actually trying to do is figure out what is the response, or what is the reward function to any action that I take. Kind of let that sink in for a minute. A lot of content. But the idea is that in the manufacturing facility, you can't take an untrained agent and let it run the pumps into the ground to figure out how the system would respond to a change in operational parameters. You need a simulated environment to get the agent really smart at operating pumps before you could ever deploy it in production. So how do you create that simulated space? How do you allow this agent to get smart without breaking the pumps or the manufacturing equipment or the motors, the fans, whatever it is, the press in the process? Well, we're proposing that you could use a generative adversarial network to simulate the environment. So we have terabytes of IoT data. So we have terabytes of vibration data and process data butted up against one another. Imagine that we took a real data set up through time, we'll say N. And what we did is we fed the real data set up through time N, and we can talk a little bit about some of the specific architectures that we could use to accomplish this. I have a couple that I can propose, but the idea is that you take a combination of a real data set, and usually you'll see like a latent space that gets fed into a generative network, and you allow the generative network to create a synthetic data point as it relates to vibration in one future time step from the current picture of the operational parameters. So let me repeat that. What we're doing is we're trying to use a generative network to say, hey, I see the state today. I'm starting out just randomly selecting what the next response is. That's the idea of starting with a latent space from a generative network perspective. And I am starting by saying randomly, this is going to be the synthetic vibrations next point, subject to the process parameters that I see today. Then what you do is you end up taking the real response, so the real vibration in this next time step, and feeding both of those together into the discriminative network that then computes your loss function. So basically what's happening is you're getting two networks competing against one another, as is kind of the general consensus when it comes to generative adversarial networks. And you're using game theory to allow the generative network to try to get smarter or as smart as the discriminative network in terms of saying, hey, this is a fake data point, and you fool the discriminative network from saying, hey, wait, which one was the real vibration and which one was a synthetic vibration? So you could start to see here how this system would get smart. So the idea here is that you have all of these training epochs. So now understand we're looking at, one single time step on one single pump asset, but the idea scales if we have a bunch of different times and we have a bunch of different assets. And the idea is subject to some process parameter, you have a synthetic vibration point, you have a real vibration point, and on each epoch, you get closer and closer to being able to predict what the real vibration response would be through some synthetic simulation. So you start to get a picture of how this could be really useful. If I now can say, hey, from my generative network, here's the current state. What's going to be the future state? You essentially have an environment where you can take simulated actions and understand how the environment would evolve. So basically what you're learning is, what's the reward function? What is the response of the state subject to any action I take? So that, as I'll get to in a second, the agent can learn the optimal policy. Now, in terms of accomplishing this, I'm going to click back real quick. There's a couple of different architectures right now today that people are starting to investigate. There's a couple of really interesting papers on something called Recurrent GAN, or Recurrent Generative Adversarial Networks, that would take in this time dimensionality. I read in one of the papers that, I'll have to look up some of the information and kind of share some papers after this, but that gated recurrent units seem to be performing better than LSTMs due to some specific kind of mathematical formulations behind it. I also propose a slightly simpler mechanism in some of the research that we've been doing. And the idea is, rather than even using any type of recurrent unit, we actually just concatenate a latent variable onto the real data set. So imagine, front and center of this, feeding into the generative network, there's like the latent space that got concatenated to that real data set. And then we set an attention unit in front of the generative network to enable it to look at specific pieces of time dimensionality. So basically the idea is that, say certain operational parameters, change the response 10 minutes from now, this attention mechanism will know to look at a different general space within the past operational parameters when trying to figure out how the system would respond from a vibration perspective. Kind of similar to the idea of using attention on like sequence to sequence models, where you're looking at specific parts of a sentence. This is the context that was important for figuring out whether we should say the next word is cat or dog. I use that as a loose example, but there are a lot of papers out there, and there's a lot of literature, starting to be a lot of literature around different adversarial network architectures for predicting the next step in a sequence, much like in this fashion. So in the last piece, I want to just kind of summarize what we talked about and kind of tie a couple of concepts together. And the idea here in the bottom left is that if we can get really good at generating synthetic data points for a future time step, we can very literally understand the reward function for that environment. We change a process parameter in a massive factory plant. We can understand this really complex nonlinear relationship in terms of how will the vibration respond, not just on this asset, but on the asset next to it. Really, really important when you think about things like resonance. If you have 3 pumps in a line, we have to maintain some flow rate across all 3 pumps. Well, I want to take one pump down a few RPMs, so I have to pick up another pump a few RPMs. And how do I take that to balance the system, maintain our production volume while minimizing vibration. So you need to know how will the system respond to operational changes. Once you have that, you can train an agent to understand the optimal policy that would allow the agent to actually minimize the vibration in real time and automatically. So I think that this is going to be a real game changer when we think about industrial automation in the next 3 to 5 years. KCF right now has the data. We're getting the format together. We're starting to work through what is the next step with this. We have a few simulations going, but I'm really bullish on the future of this technology, and I would love to hear other papers that people have read that they think are really intriguing. You know, what you guys see as drawbacks. You know, what are the challenges you think that we'll face on this path, and ultimately just have a great intellectual conversation about it. I think that it's a really fascinating topic, and you know, I think it's going to have a real impact in the next 3 to 5 years. So I appreciate everyone's time. Thanks for watching, and please let me know if you have questions or are interested in any of these topics.